Okay, welcome to the second lecture of Laplace transformation. In the last lecture, we did up to the basic concept of Laplace transformation. So today's topic is first shifting theorem. First shifting theorem. What this theorem is saying? If Laplace transformation of the function ft is say known to us, say it is fs, then the Laplace transformation of e to the power at into ft is simply f of s minus a, or if it is the case e to the power minus at ft, then it is f of s plus a. For example, if I consider the case, I have to find the Laplace of e to the power minus t into sin t. So please note that in order to apply this first shifting theorem, we need to have one of the function as exponential function and other function is from the list of the formula that I had given in my lecture number 1. So we know that the Laplace of sin t is 1 by 1 plus s square. Therefore, Laplace of e to the power minus t ft according to that result, that is second one, s plus 1, because a is here 1 if I take this situation, then this is my fs, this is my fs, so therefore, and if I take my ft as sin t, so therefore Laplace of e to the power minus t of sin t will be equal to 1 upon 1 plus s perfect square. This will be the answer. So it means that by using this theorem we can find the Laplace transformation of several such functions. For example, suppose I have to find the Laplace of t into e to the power minus t. Again, Laplace of t is 1 by s square. So therefore, Laplace of t into e to the power minus t simply 1 upon s plus 1 whole square. That is, replace here s to s plus 1. Okay, this is the simple substitution. One more example that I can give you, if I have, instead of this, if I have to find the Laplace of e to the power 2t into, say, t to the power n. We know that the Laplace of t to the power n is gamma n plus 1 upon s to the power n plus 1. So what I will do here, replace s by s minus 2. So therefore the Laplace of e to the power 2t into t to the power n is simply gamma n plus 1 upon s minus 2 whole to the power n plus 1. So I think now it is sufficient to understand the application of this. Now the next part is what is the proof of this theorem. That is also somewhat logical. Now, proof. See that. I will prove this part and then the second part is same as that of this part. Proof. By definition, L of e to the power at into ft by basic definition is 0 to infinity e to the power minus st e to the power at ft dt. By definition. It follows by definition, which is nothing but definite integral 0 to infinity. I can write e to the power minus s minus a of t into f of t. Okay, can I take s minus a, another symbol, say v, 4 times left. So then it will become 0 to infinity e to the power minus vt into ft dt. Now what is this? This is f of v. And what is v? F of s minus a. Because we are integrating with respect to t, so therefore here v will be a parameter, so therefore the Laplace transformation of this will be f of v, that's simply function of v, but we have replaced v by s minus a. So this proves this first shifting theorem. So now another result that is also really important. Now understand that result also. Suppose, before giving you another result, I want to ask you one question. That is what we call review. Suppose I have to integrate a function from a to b, and which is a function of x and alpha dx. Then can I assume that since we are integrating it with respect to x, so alpha will be constant, so it will be entirely a function of alpha. If it is a function of alpha, then we define g prime alpha as simply a to b del by del alpha of f of x comma alpha dx. Please note that this rule is known as the Leibniz rule. Leibniz rule. Now the important thing is that you must be thinking that here I am writing ordinary differential and here as partial differential. Since it is a function of x and alpha, function of two variables, so therefore the partial differentiation will come. Okay, now a little bit review so that you can feel this concept. Suppose if I give you this example, say this example is, suppose I have to integrate 1 to 2 alpha x dx, so that it is alpha x square by 2 1 to 2, which is simply alpha of 2 minus 1 by 2 3 by 2 of alpha. So again it is a function of alpha. So this will imply I can say that 1 to 2 alpha x dx is g of alpha, and g of alpha is 3 by 2 of alpha. Now what is g prime alpha according to this? It is 3 by 2. Now if I want to write according to my concept, g prime alpha will be 1 to 2 del by del alpha of alpha x dx, which is 1 to 2. What is the partial differentiation of this x dx? Which is x square by 2 1 to 2, which is again 2 minus 1 by 2 3 by 2. So this satisfies the concept that I had given to you. So it means now it should be justified that whatever concept I did with you, so I think you should be in the position to agree with that concept. Okay, now what is the instant application of this result? Now see that. Suppose I am having Laplace of ft, which is f of s. Now what I want to find? To find Laplace of t to the power n into ft, where n is a positive integer. Please mind it, I am writing positive integer. So now let us understand this concept also. Now by basic definition, L of ft is simply, which is same as f of s, 0 to infinity e to the power minus st ft dt. Now if I differentiate it, d by ds of fs, so by Leibniz rule it will be 0 to infinity del by del s of e to the power minus st ft dt. So it is by Leibniz rule. So now this is nothing but 0 to infinity, can I write say as minus t e to the power minus st ft dt, because I am partially differentiating it. So this is d by ds of fs. Now if I continue like that, what will be d2 by ds2 of f of s? Again I will write 0 to infinity del by del s of all of this quantity minus t e to the power minus st ft dt. What is this? It is 0 to infinity minus t perfect square e to the power minus st ft dt. Okay, it is like that. Okay, continue like that. So what it will be the dn dsn of f of s? It is simply, from this argument I can generalize that it is minus t whole to the power n e to the power minus st ft dt. It is like that. Now I think it is the time to generalize this result. Okay, and now in order to generalize it, I am removing first few lines of this proof. Okay, like that. I have removed. Now from this, let it be star. From star, dn by dsn of fs is simply, I can say that it is minus 1 to the power n outside 0 to infinity t to the power n e to the power minus st ft dt. Can I write this as minus 1 to the power minus n dn dsn of fs, which is same as 0 to infinity t to the power n e to the power minus st ft dt. Now what is this? This is Laplace of t to the power n into ft. So this is the result that we have established. It means that now before getting to the main conclusion, I want to write the main format of this. So we have established this thing here. Okay, now let us understand the main concept. Now what we have generalized, I am writing the generalized version of this proof. That is, if L of ft is say fs, then L of t to the power n into ft is minus 1 to the power minus n dn by dsn of fs. It is a very interesting result, and please note that n is a positive integer, so that I had mentioned. Okay, now for example, suppose I have to find the Laplace of t into sin t. Now I know that Laplace of sin t is 1 upon 1 plus s square, which is my fs. So now by this result, Laplace of t into sin t, now here n is 1, so it will be minus d by ds of 1 upon 1 plus s square. If we differentiate it, it is simply 2s upon 1 plus s square whole square. So it means that if you have to multiply it by t, then you have to differentiate it 1 minus times of 1 times. If you are multiplying it by t square, then double derivative of the Laplace transformation. So it depends on if you are differentiating, if you are multiplying by t to the power n. If n is odd, then minus times of that much derivative, and if n is even, then plus times of that much derivative. For example, suppose I have to find the Laplace transformation of, say, t cube into cos hyperbolic t. So I know that Laplace of cos hyperbolic t is simply s upon s square minus 1. Is that okay? Now, so therefore Laplace of t cube into cos hyperbolic t is simply minus d3 by ds cube of s upon s square minus 1. It is like that. Differentiate it simply 3 times by using quotient rule, you will get the desired result. Okay, now let us move ahead. Now my next question is, what is the application of these results in integration? Suppose my question is, evaluate integral 0 to infinity t into sin t into e raised to power minus t dt. Now if I use a traditional way of integration, I think it will be a bit lengthy problem. So now if I take ft as t into sin t, then L of ft that we have found in the last example was 2s upon 1 plus s square whole square by multiplication rule, by multiplication by t to the power n. But by definition of LT, L of Ft is 0 to infinity e to the power minus st Ft dt, and which is equal to Fs, and Fs is 2s upon 1 plus s square whole square. So therefore this will imply Laplace of t into sin t, which is 0 to infinity e to the power minus st t into sin t dt is 2s upon 1 plus s square perfect square. Okay, now see that what is the similarity between this integral. It is almost same except at this place. If I take s is equal to 1, then this will imply integral 0 to infinity e to the power minus t into t sin t dt. S is 1, 2 upon what it will be? By simply 4. So value of this integral is 1 by 2. So hence the value of this integral is 1 by 2. So it is as simple. So therefore by using Laplace transformation you can get the value of such type of integrals also. Okay. So this is the application of this Laplace transformation in the integrals. Now my next question that is also equally important. Now see this also. Now what I want to prove that, the question is prove that is if L of Ft is say Fs, and then the question is prove that L of Ft by t is the integral s to infinity Fs ds. Okay, this thing we want to establish. I will proceed by right hand side. Take right hand side. Integral s to infinity Fs ds. Can I write this as integral s to infinity? What is Fs? Which is L of Ft ds, which is nothing but s to infinity integral 0 to infinity e to the power minus st Ft dt ds. Now it is a problem of double integral. Now what I will do, I can write this as 0 to infinity integral s to infinity e to the power minus st ds, and then Ft dt, which is nothing but 0 to infinity e to the power minus st by minus s, then s to infinity Ft dt. Now what is this? It is nothing but integral 0 to infinity 0 minus into 1 by s. Okay, now say, sorry, it is not minus, it is minus 1 by t, because since we are integrating it with respect to s minus 1. So here also it is minus 1 by t, because at infinity it is 0, at s it is simply, I think it will be e to the power minus st, like that, and it is entirely like that, Ft dt, which is nothing but 0 to infinity. I can write that e to the power minus st Ft by t dt. Now what is this? It is the Laplace of. So it is nothing but L of Ft by t. So this proves this result also. Now the next is, what is the instant application of this result? Now that is also important. Now let us talk about the application of this. Suppose the question is find L of sin t by t. We know that L of sin t is 1 upon 1 plus s square, which is my Fs. So therefore by the result that we have done, Laplace of sin t by t is simply s to infinity fs ds, which is s to infinity ds by 1 plus s square, which is nothing but tan inverse s to infinity, that is tan inverse infinity minus tan inverse s, which is nothing but pi by 2 minus tan inverse s, which is same as cot inverse s. Please note that while proving it, I will taking this rule as my help, integral s to infinity fs ds. It is like that. Okay, so we call this rule as division by t. We call this rule as division by t. Okay, now one more example. One more example of this type. Okay, suppose if I ask you what is the value of this integral 0 to infinity sin t by t dt. Again, we know that the Laplace of sin t by t we have found in this earlier example as pi by 2 minus tan inverse s. So therefore, L of sin t by t will be simply, by definition, 0 to infinity e to the power minus st into what is ft sin t by t dt is equal to pi by 2 minus tan inverse s. As s is my parameter, if I take s is equal to 0, then this will imply integral 0 to infinity e to the power, that is 0t, in fact, yes, 0 times of t sin t by t dt, which is same as integral 0 to infinity sin t by t dt, which is simply pi by 2, because tan inverse 0 is 0. So the value of this integral is pi by 2. So now, up to now, we had done the 3 results. Now I am summarizing those 3 results. I am summarizing those 3 results. The first was L of e to the power at into ft is f of s minus a, and the second was L of t to the power n into ft is minus 1 to the power n dn by dsn, or say minus n, of f of s, where n is a positive integer. And third one was L of ft by t is simply integral s to infinity fs ds. This rule is known as the division rule. This is known as the multiplication rule. By t to the power n, and here by t. It is like that. So now, up to this part we have covered now. Now, this is the end of the Laplace series lecture 2. So now we will continue in the third lecture. So okay, thank you for this lecture.